Welcome back. We are on lecture 3 of Fundamentals of Inorganic Glasses. We're getting started now with chapter 2 in the book, which deals with fundamentals of the glassy state. Today, what we're going to do is cover the definition of glass, including many of its nuances. I hope at the end of this lecture that you'll be able to understand what makes a glass and how it is different from other states of matter. So let me share my screen and I will switch over to our presentation. So what is a glass? What I would like to do is start off by reading this definition of glass on the left. It's not going to make a lot of sense at first, but then we're going to spend quite a bit of time going through the details of this diagram on the right, which is called the volume temperature diagram. And after understanding those details, we'll return back to the definition of glass, and hopefully at that point in time, the definition will make sense. So let's start by reading the definition. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes towards the liquid state. Whatever do you mean, Dr. Barrow? Let's find out. So let's walk through this step by step. So turning our attention now to this volume temperature diagram, this is the single most important diagram in the field of glass science, because this volume temperature diagram encapsulates what it means to be a glass, where glasses come from, and how glasses are different from other states of matter. So let's walk through this step by step to try to understand why. So what we have here is that the volume of a material here is on the y-axis, and the temperature is on the x-axis. And what we're going to do is start off at this point here, this point labeled lowercase a. This is at high temperature and high volume, and this is in the liquid state. So the equilibrium state of matter at this point A is the liquid. Now, as the liquid is cooled, it moves from the right to the left because temperature is going down as you go from the right to the left. And as it's cooled, it will go from this point A down to this point B. So the volume is shrinking as the liquid is cooled. And this is expected because if the liquid has a thermal expansion coefficient that is positive, that means the volume would expand as the temperature goes up, and the volume would contract as the temperature goes down. So in going from this lowercase a to lowercase b, we're lowering the temperature and the liquid contracts, lowering its volume following the thermal expansion coefficient of the liquid. Now, what normally happens is if you're at this point B and you cool slightly below this point B to the point C in this shaded region here, this shaded region falls just below the melting point of that particular system. This is labeled as Tm here. T with the subscript m indicates the melting point. And if you cool the liquid just slightly below the melting point, then there is a thermodynamic driving force for the liquid to crystallize, because now the most thermodynamically state of matter is no longer the liquid at those low temperatures, but rather the crystal. And so in order to stay in equilibrium, in this shaded region here, the liquid would undergo a first order thermodynamic phase transition, which means that it undergoes this discontinuous change, or this big jump here in volume. It also undergoes a similar jump in enthalpy and in entropy. All of these first order thermodynamic variables, the volume, the enthalpy, and the entropy, they all undergo a discontinuous change for this first order thermodynamic phase transition. This is just a normal freezing process. So the liquid is cooled below the melting point of the corresponding crystal. It becomes thermodynamically favorable to crystallize, and therefore the atoms in the liquid state rearrange themselves in order to form an ordered crystal structure. So when that happens, that takes us down here near this point D, down to the crystal line. And if you continue to cool the crystal, then the crystal will contract according to its thermal expansion coefficient, and going from point D all the way down here to point E. You'll note here that the slope of the crystal line is quite a bit more shallow compared to the slope for the liquid line. that means that the thermal expansion coefficient of the crystal is lower than the thermal expansion coefficient of the liquid, so it's not contracting as much for the same change of temperature. So this is what happens in equilibrium, and this is something that we're all familiar with from our high school physics classes, right? So a substance will undergo a phase change when it becomes thermodynamically favorable to do so. Whichever phase has the lowest Gibbs free energy would be the equilibrium phase. So in this case, the crystal has the lowest Gibbs free energy all the way from point E to point D, and actually at temperatures lower than point E as well. But at the melting point by definition is where the Gibbs free energy of the crystal state is the same as the Gibbs free energy of the liquid state. In other words, the crystal and the liquid are in equilibrium with each other at that one melting point, Tm. So if you take the crystal and you heat it just slightly above the melting point, that's when the melting will occur, and that's where you would obtain the liquid state again. So one question is, why is it that the liquid crystallizes slightly below the melting temperature of the crystal rather than at the melting temperature itself? And the reason is because at the melting temperature itself, the Gibbs free energy of the liquid is the same as the Gibbs free energy of the crystal. So there's no thermodynamic driving force for the liquid to crystallize since the Gibbs free energy is the same between both phases. It's not until you cool the liquid slightly below that melting temperature that the Gibbs free energy of the crystal becomes less than that of the liquid, and that's when the crystallization would happen. Now, all of this is assuming that we're staying in equilibrium, but the fact is that it takes time for the atoms in the disordered liquid state to rearrange their structure to form the perfect crystalline order that is needed for the liquid to crystallize. In some liquids, this cools rather rapidly. For example, with water, the individual water molecules in liquid water can flow quite freely. Water has a fairly low viscosity. In other words, it's highly fluid at or slightly below 0 degrees Celsius, where it becomes thermodynamically favorable for it to crystallize. As a result, it's very easy for water molecules to rearrange themselves into a crystalline ice configuration. And then the freezing of the liquid, the crystallization of liquid water, happens quite readily. Other liquids, like liquid silica, for example, have much higher viscosities, or in other words, much lower fluidities at their melting temperatures or slightly below the melting temperatures of the corresponding crystals. And what this means is that the atomic motions are a lot more sluggish in these higher viscosity liquids like silica. In other words, it takes a lot more time for the atoms in silica to rearrange themselves to be able to form a perfect crystalline lattice. And because of this, it may be possible to take liquid silica or any other liquid that has sluggish enough kinetics and cool it fast enough through this shaded region here, through this C region, to get down into what's called the supercooled liquid regime. In other words, this gray area here that is shaded just below the melting point, this is where crystallization is most likely to occur, because this is where you have both a thermodynamic driving force for crystallization, because the Gibbs free energy of the crystal is less than that of the liquid at this point, and the kinetics of the crystallization process are fast enough for you to actually observe it. But if that crystallization is so sluggish that you're able to cool through this regime fast enough that you don't give the atoms in the liquid enough time to rearrange into a crystalline configuration, then you get another phase, which is called the supercooled liquid phase. The supercooled liquid, by definition, is just any liquid that is cooled below its normal freezing point. From a thermodynamic point of view, the supercooled liquid is not the equilibrium state. If you look at this temperature here, the equilibrium state at that temperature would be the crystal. It's the crystal that has the lower Gibbs free energy compared to the supercooled liquid. The supercooled liquid is not the equilibrium phase, but it is a metastable equilibrium phase. Metastable meaning that it is unable to lower its Gibbs free energy anymore unless it undergoes a drastic change in structure, or in other words, undergoes a phase transition in order to crystallize. So the supercooled liquid, if you just leave it here unperturbed, it's going to be stable. It's not going to change on its own. However, if it's given enough energy to be able to rearrange its atomic structure to crystallize, eventually it would undergo a first order phase transition and then drop down below here to the crystalline. Okay, so a supercooled liquid is the metastable equilibrium. The crystal is the equilibrium. What happens now if we take this supercooled liquid and we continue to cool it even further? As we take the supercooled liquid down in temperature, as the temperature of the system is lowered, the viscosity of that supercooled liquid is increasing, and it's increasing by orders of magnitude. It's going from something that's a lot more fluid to becoming much lower fluidity. So it's, instead of flowing like water, for example, it's going to flow like honey or flow with an even higher viscosity than that. So as the supercooled liquid is cooled, the viscosity continues to go up, which means that the motion of the atoms in that supercooled liquid become slower and slower. Now, eventually what happens is those atomic motions become so slow that the atoms are moving, or they're flowing on a time scale that is longer than the time scale of our experiment. So it's longer than the time scale of, say, pouring a liquid out of a crucible, for example. When that happens, the system undergoes what's called the glass transformation or the glass transition. This is not something that occurs at one specific temperature, but rather something that happens over a range of temperatures, as indicated by this curly brace shown here. Sometimes you'll see this labeled as the glass transformation range. Sometimes you'll see it labeled as the glass transition range. They both mean the same thing. Now, when this happens, this is not a thermodynamic phase transition. It's not like going between a liquid and a crystal where there is an abrupt change of properties. Instead, what happens in the glass transition or the glass transformation is that there is a gradual freezing in of the supercooled liquid structure. So if you've got this disordered liquid structure of the supercooled liquid, and it's being cooled down, it's taking longer and longer and longer for the atoms to be able to flow. Eventually, they become kinetically frozen into their liquid-like structure. As this happens, as this gradual freezing in process happens, this corresponds to the glass transition range. And then what we end up with is down here on the left-hand side, we have a material that has the atomic structure that's like that of a liquid. It's got the disordered non-crystalline structure of a liquid, but for all practical purposes, on the time scale that we are observing it, or on the time scale of the experiment, that material behaves like a solid. And this is what we all know and love as the glassy state. So the glass is down here at either these points G or H. We'll get to the difference between them in a moment. But one of the key things about the glass is that the structure of the glass is continuously connected to the structure of the liquid. In other words, the short-range atomic ordering of the glass and the lack of any type of long-range order, all of that points back to the supercooled liquid state. So the glass has a structure that is very close to that of the liquid structure. But because the atoms are in a frozen-in configuration, if you tap on the glass, if you hit it with a hammer or something, the way it behaves mechanically is like a solid. So it has some liquid-like features, like its non-crystalline structure. It has some solid-like features, like its mechanical properties. And it's falling, somewhere in between the two. And what we're going to learn today is that glass not only inherits some properties of the liquid state and the solid state, but it also has its own unique properties as being a glass. And one of those is because of its non-equilibrium nature. So let's suppose here that we are at one of these low temperatures. The equilibrium phase is the crystal. The supercooled liquid, if you continue the supercooled liquid line down, this is the metastable equilibrium. What does that make glass? It's neither the equilibrium nor the metastable equilibrium. Glass is, in fact, an unstable phase. It is a thermodynamically non-equilibrium phase. And what this means is that the glass itself is unstable. It appears solid, it appears rigid and non-flowing on the timescales that we normally observe it. But if you were to wait long enough, you would observe that over time, this glass is actually very slowly, continually relaxing towards this supercooled liquid line here. So if you take this glass here, and let's suppose that you hold it at a temperature shown here, and just hold it there for a very long period of time, over time, this volume of the glass being held at this constant temperature is going to shrink and shrink and shrink and shrink until it converges to this supercooled liquid line. That's because glass is a non-equilibrium material, and there's going to be very slight rearrangements of the structure that occur over time that will drive it towards the supercooled liquid state. Now, when we observe most common glasses at room temperature, we don't see this happening because the timescales that are involved with this relaxation occur over more than billions or trillions of years. It occurs on a timescale that's much longer than the age of the universe. And so what we're doing when we're observing glass is catching kind of a kinetically arrested state that exists only because we are observing it on a time scale that is much faster compared to the time scale required for the atoms in the glass to flow. So this is all a byproduct of this being a thermodynamically non-equilibrium state. This glass transformation range or glass transition range itself, as I mentioned, is not a thermodynamic phase transition. There's no thermodynamic phase transition between the supercooled liquid and the glass. Instead, what this is a kinetic transition. It's a kinetic transition because the kinetics of the atomic motions in the supercooled liquid are becoming slower and slower and slower as it's being cooled. And eventually those kinetics become much slower than the time scale that we are observing it on. And when that happens, it's this gradual freezing in process. As the atoms become frozen, that's what gives us the glassy state. Now, another byproduct of the glassy state being non-equilibrium is that the final properties of the glass depend on more than just the chemistry of the glass and the temperature and the pressure. It actually depends on the entire thermal history and, if applicable, also the entire pressure history of the system. For example, if we draw a vertical line through the figure here, what you'll see is that there's two different glasses represented on this plot. One of these that's labeled as the fast-cooled glass, and then the other one lower down, which is labeled as the slow-cooled glass. These glasses both have the same chemistry. They both came from the same supercooled liquid state. They both have the same chemistry. And if you draw a vertical line through these, that vertical line corresponds to the same temperature. But what you can see is that they have different volumes. The fast-cooled glass has a higher volume compared to the slow-cooled glass. Why is that? If we go back to where the glass comes from, in both cases, the fast-cooled glass and the slow-cooled glass come by the supercooled liquid undergoing a glass transition. In the case of the fast-cooled glass, if you take your supercooled liquid here and you quench it very rapidly, meaning that you lower the temperature of the supercooled liquid very rapidly, you're giving the system less time to stay in its metastable equilibrium. The faster you cool the supercooled liquid, the less time the supercooled liquid has to be able to adjust to those new temperatures as it's being cooled. And as a result, the supercooled liquid, when it is cooled quickly, will fall out of equilibrium at a higher temperature because you've given it less time to equilibrate. And if it has less time to equilibrate, then it will undergo this kinetic transition at a higher temperature. On the other hand, if you take a supercooled liquid and cool it more slowly, if you're cooling the system more slowly, then you're giving it more time to find its new equilibrium at each new temperature as the temperature of the system is lowered. So if the supercooled liquid is cooled slowly, it's able to stay on this supercooled liquid line, shown here, stay in this metastable equilibrium, and it only falls out of this metastable equilibrium at a lower temperature when the time scale becomes long compared to its relaxation time scale. So for the slow cooled system here, this is able to stay in equilibrium down to lower temperatures, that falls out of equilibrium at lower temperatures, and has this slow cool line shown here. So one of the other byproducts of glass being in non-equilibrium state is that this thermal history matters. You'll see the fast cooled system undergoes the glass transition at a higher temperature and therefore ends up with a higher molar volume compared to the slow cooled system, which is able to stay in its metastable equilibrium down to a lower temperature regime. It undergoes the glass transition at a lower temperature regime and then freezes into a glass with a lower molar volume. So two different glasses here that are both the same chemistry at the same temperature, but because they experience different thermal histories, they end up with different properties. So this is very interesting. And it also means that that we need to have an additional thermodynamic parameter to describe the state of the glass. It's not like a crystal, right? With a crystal, if you're in equilibrium, the entire state of the crystal is defined by its chemistry and its temperature and its pressure, assuming that you're at equilibrium. There's only one possible state that it could be in. With the glass, there are an infinite number of possible states that the glass could be in, depending upon the different cooling pathways that you could take. And what this means is that you can tailor the properties of the glass, not just by changing the composition of the glass, but also by changing its thermal history. And although this figure here shows the volume temperature diagram, and what I'm explaining this is in terms of the volume, meaning that the volume of the system is changing, every other property of the system is also changing. Obviously, if the volume changes, then the density changes. This also means that the Young's modulus is changing. The viscosity of the glass is changing as well. Every single property of the glass is changing as the thermal history changes. Now, if it's not enough to just have the chemistry of the glass, the temperature, and the pressure, that's not enough information to be able to define the state of the glass. That means we need to introduce another thermodynamic parameter. Now, the easiest, simplest thermodynamic parameter to introduce is what's called the fictive temperature, or labeled as TF. T subscript F, as shown here, this is TF1. This TF1 corresponds to the fictive temperature of the slow-cooled glass, and then TF2, which corresponds to the fictive temperature of the fast-cooled glass. So the subscript F stands for fictive. Fictive literally means fictional. It is a fictitious temperature. It's not a real temperature, but what it is an additional thermodynamic order parameter that gives us more information about the state of the glass by telling us something about the thermal history of the glass. And there are multiple ways to get fictive temperature, but the way that is most commonly used is you take the glassy line on this diagram. So here is the glassy line. And if you extrapolate that line and see where that line intersects with the supercooled liquid line, that point of intersection, if you drop this down to the temperature axis, that point of intersection is the fictive temperature for that glass. So for the fast-cooled glass, you take this fast-cooled glassy line, extrapolate that as a straight line, see where it intersects with the supercooled liquid line, drop that down to the temperature axis, and that is the fictive temperature of your fast-cooled glass. For the slow-cooled glass, let's do the same thing. So we take the line here for the slow-cooled glass, extrapolate it until it intersects the supercooled liquid line, drop that down to the temperature axis, and this is what gives us TF1. And you'll see that TF1 is at a lower temperature compared to TF2. The fact that these two fictive temperatures are different from each other tells us that the thermal history of these two glasses is different. And what the fictive temperature indicates, it's kind of an approximation of where the glass has fallen out of equilibrium from the supercooled liquid state. So for this fast-cooled glass, note that as the supercooled liquid is cooled, this glass transition process or glass transformation process occurs over a range of temperatures. It's a gradual freezing in process, and we are simplifying that by introducing a fictive temperature that says, okay, within that range of temperatures, let's pick one of them, this fictive temperature where these lines intersect, and that is approximately where the supercooled liquid has been frozen into the glassy state. So for a fast-cooled system, that happens at a higher temperature compared to a slow-cooled system. And as a result, the fictive temperature of the fast-cooled glass, TF2, is higher than the fictive temperature of the slow-cooled glass. And this difference of fictive temperature is what explains the differences in the volume between the fast-cooled glass and the slow-cooled glass. All right, so glass is special because it is non-equilibrium, which means that its properties depend on the thermal history, which means that it is continuously trying to relax towards the supercooled liquid state, and we need an additional thermodynamic parameter to describe the state of the glass. One other thing I'll note is this little dashed line that's shown here. So for the slow-cooled glass, this dashed line is meant to represent what if you take the slow-cooled glass and heat it back up. As you heat it back up, the reheating curve of the glass never retraces the initial cooling curve. And that is another byproduct of the glass being non-equilibrium, is that if you take this back up in temperature, there's a hysteresis there. It's never going to retrace the same path because of the glass trying to converge back to the supercooled liquid state. All right, so let's now go back to our definition of glass and read it one more time and see if it makes sense in light of our discussion about the volume temperature diagram. So glass is a non-equilibrium. Non-equilibrium, meaning that it is thermodynamically an unstable state. We know that the crystal is equilibrium, the supercooled liquid is the metastable equilibrium, and glass is unstable. So glass is a non-equilibrium state. So this is telling us something about the thermodynamics of the glass. So glass is non-equilibrium and it's non-crystalline. Non-crystalline meaning that the structure is lacking any type of long-range order. So the atoms in a glass have the structure of a liquid. They don't have the structure of a crystalline solid. So this is what non-crystalline indicates. So glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale. Why does it appear solid? The structure is like a liquid, but if you tap on the glass, it responds like an elastic solid would respond. And the reason is that when you're tapping on the glass, you're probing the glass on a very short time scale compared to the time scale that it takes the atoms in the glass to flow. And as a result, the atoms in the glass don't have enough time to rearrange their structure in response to you tapping on it. And therefore, the response that you get from the glass is a solid-like response from that mechanical point of view. So that's what it means by saying that it appears solid on a short time scale, but it continuously relaxes towards the liquid state. So this glass, if you wait long enough, if you give the system enough time where the kinetics can actually happen, over a very long period of time, this the structure of the glass will rearrange itself to approach that of the supercooled liquid. Because as the glassy state is approaching the supercooled liquid state, it is getting closer to its metastable equilibrium. As that's happening, there's a continuous decrease in the Gibbs free energy of the system. That decrease in the Gibbs free energy of the system is what is enabling it to get closer to equilibrium. So glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes towards the liquid state. So I want to make sure that everyone understands all the details of what we discussed here, because this is foundational to the rest of the course. If there's anything that you don't understand about what we discussed, please ask questions in the comments down below, or read through chapter 2 in the book, or go back and rewatch this part of the lecture. I just want to make sure that nothing is unclear about this particular slide. All right, once everything is clear, we will move on for an example that my advisor, Dr. Varshnaya, the co-author of our book here, the example that he likes to give about glasses versus amorphous solids, and how they relate back to liquids and crystals. And he considers an example of let's say, a chalkboard eraser here, that if you were to lay it flat on the desk, let me just use the book as an example. If you lay this flat on the desk, there is a configuration of, in this case, the book, that corresponds to the lowest free energy of the system. So it would be the lowest potential energy of the system by placing the book like this. And this is this corresponds to, or is analogous to, the crystalline state. Now, the metastable supercooled liquid state would correspond to, instead of having the lowest energy state like this, you would tip this up on its side, like this, for example, where this, if you leave it alone, it's not going to move. So it's metastable. But is this the lowest energy configuration? No, because if you knock it, you can tip it over. If you perturb the system enough, it can find a lower energy configuration by knocking it over. So this is what represents the metastable state, or a metastable state. The supercooled liquid is one particular metastable state. For example, maybe having the book on the desk like this. So this is metastable because if you just leave it alone, if you don't perturb it at all, it's not going to move. But if you knock it over, it could crystallize by finding a lower energy state. The glass is non-equilibrium with respect to the supercooled liquid, so the glass is continuously relaxing towards the supercooled liquid state. So the glass is, if you take this supercooled liquid, and let's suppose that we tilt it up like this. When you tilt it up like this is unstable. So over time, it is continuously relaxing towards the supercooled liquid state, as shown in this diagram here. So this glassy state is unstable, and it's continuously relaxing towards the supercooled liquid, and that supercooled liquid is in turn metastable with respect to the crystal. So those are kind of the three different levels of stability here. The unstable glassy state, and this is going to relax towards the supercooled liquid state, and that is metastable, and when that gets perturbed, eventually it could crystallize. What then is an amorphous solid? A lot of people incorrectly will use the terms glassy and amorphous interchangeably. The reality is that glasses and amorphous solids are two different phases of matter, and they are not interchangeable. They are both examples of non-crystalline materials. The difference is that the glass comes from the supercooled liquid state. It's continuously connected to the supercooled liquid state by the glass transition. Its atomic structure is very similar to that of the supercooled liquid. An amorphous solid, on the other hand, has a non-crystalline structure that is completely decoupled from the structure of the liquid state. Normally, amorphous solids could be made, for example, through a vapor deposition process, where its atoms being deposited directly from the vapor, and then they adopt a structure which may be non-crystalline, but it is completely different from that of the liquid state. And as a result, amorphous solids do not exhibit a glass transition. So glasses and supercooled liquids are always connected to each other through the glass transition. If you heat it up, you can become a supercooled liquid, cool it back down through the glass transition, and it becomes a glassy state. That can happen because the structures of the supercooled liquid and the glass are so similar. With an amorphous solid, on the other hand, the structures are decoupled. There's a very different structure of the amorphous solid compared to the liquid state. And as a result, amorphous solids do not have a glass transition, and they cannot be formed by quenching from a liquid. So this is really a key difference, that the structure of the amorphous solid is very different from that of the structure of the liquid. Amorphous solids do not undergo a glass transition, whereas glasses do undergo a glass transition, and amorphous solids cannot be made by quenching from the liquid state. Amorphous solids are unstable with respect to the crystal, and what this means is that over time, the amorphous solids are going to relax directly to the crystalline state rather than glasses relaxing directly to the supercooled liquid state. So what you should take away from this slide is that there are two different distinct types of non-crystalline materials that are either solid or solid-like. Amorphous solids and glasses. And these are two distinct classes of material that should not be confused with each other. Now, one minor point here on this slide is that a couple of systems, a few different chemistries have anomalies in their volume temperature diagram. And two of the most common ones are two of the most common substances found on Earth, namely silica, SiO2, and water. With both silica and water, they have an anomalous volume temperature diagram because if you look at the supercooled liquid line here, so this is the liquid line, and then let's suppose the crystallization is happening here. This would take us to the thermodynamically stable crystalline state. But if you quench the liquid fast enough to get into the supercooled liquid state, the supercooled liquid volume is actually shrinking here. And then at some point, it turns around and then the volume goes up in the other direction. Silica is known to observe this or to exhibit this behavior. Water is a common example of exhibiting this behavior, except that the crystallization line in the case of water would be over to the left here. So it's well known, for example, that water actually has its maximum in density or its minimum in volume at about 4 degrees Celsius, which means as you cool liquid water down, it's shrinking and shrinking and shrinking until you get to about 4 degrees Celsius. And then the volume of the water starts to expand again when you cool it below 4 degrees Celsius. And this is good for us because the colder water is expanding and it's rising up as it's being cooled. Ice, of course, is anomalous in that it has a lower density compared to liquid water, so higher volume compared to liquid water, which means that lakes and ponds and so on freeze from the top rather than freezing from the bottom, which of course is good for supporting life on the planet. So we're all beneficiaries of this. But it is, an additional complication we have to deal with the volume temperature diagram. So in the case of water, this minimum in volume occurs around 4 degrees Celsius. So if you cool the liquid state fast enough that you can undergo the glass transition at temperatures higher than 4 degrees Celsius, then you'd have this type of behavior here where the faster cooled glass has a higher molar volume compared to the slower cooled glass, which is what we expect. But if you cool the system slower so that the glass transition occurs at temperatures below 4 degrees C, then you're in this anomalous regime where the slope of the volume temperature diagram has changed. So in this regime here, the ordering of fast and slow cooling have switched. So fast cooling still always undergoes the glass transition at a higher temperature compared to slower cooling, but the faster cooled glass in this regime would have a lower volume compared to the slower cooled glass. And this all goes back to the anomalous behavior of the supercooled liquid state. Like I said, silica behaves the same way. So you can quench silica in a regime that has the normal behavior on the right-hand side, or quench silica in this anomalous regime, in this slower regime, which flips the order of the molar volume versus cooling rate. All right, so to summarize this lecture, glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes toward the liquid state. The glass transition is a continuous kinetic transition between the liquid and glassy states. The non-equilibrium state of the glass is described by its fictive temperature, and a glass exhibits a glass transition, an amorphous solid does not. So yes, if there are any questions, please ask. Please don't be shy. And next time, when we move on to the next lecture, we are going to deal with the second part of chapter 2 in the book, which deals with more fundamentals of the glassy state. All right, thanks everyone. I'll see you next time.